Hi everyone, I'm Martin Lee and I will present our work on towards streaming perception. This is joint work with Yuxiong Wang and Deva Ramanar. This work is about different ways to think of evaluation for real-time online perception, which we refer to as streaming perception. To be more specific, in streaming perception, data arrive in a real-time stream and the algorithms only have access to inputs until current time. In this work, we focus our study on embodied perception, which refers to the setting that autonomous agents need to perceive its environment so they can act or react in time. Accuracy and latency are two important metrics to evaluate computer vision algorithms. In embodied perception, accuracy and latency are always at odds. A more accurate algorithm usually implies a higher latency. The standard way of evaluation is to plot accuracy against runtime. While such a plot is good for offline evaluation, we found that it fails to capture some properties that are unique to embodied perception or real-time applications. To see this discrepancy, let's look at the sensor stream first. At the first time instant, the sensor takes a snapshot of the world and the algorithm begins processing this observation. At the second time instant, the algorithm finishes, but the state of the world has already changed. Considering this observation, we propose a metric and a meta-benchmark to better evaluate computer vision algorithms in the streaming setting. The key insight for our benchmark is that we evaluate the output of perception algorithms at every time instant. And this forces the algorithms to consider the amount of streaming data that should be ignored while computation is occurring. To define the metric, we need to define ground truth and prediction pairs. The ground truth is the same as in the standard offline setting, but the prediction is different. For ground truth at time t, instead of pairing the prediction for frame t, we pair it with the most recent prediction at time t, denoted by phi of t. The central idea is that we align ground truth and prediction using time instead of an input index. Now let's take a closer look at the alignment. The algorithm can have many prediction outputs. It can even have intermediate predictions within the processing block, as done in many progressive algorithms. Each prediction is paired with a timestamp. Given a benchmark query at time t, phi of t is the prediction index with the largest timestamp before time t. This is the real-time constraint in our benchmark. After we have collected our ground truth and prediction pairs, the benchmark applies the original test metric for streaming evaluation. For example, the metric can be classification accuracy, detection average precision, or segmentation mean IOU. Therefore, by definition, our meta-benchmark generalizes to all single-frame tasks with their existing metrics. And this is the reason that we call it a meta-benchmark. Our view of real-time processing is quite different from existing real-time algorithms or anytime algorithms. Those algorithms compute on a contract. The algorithm must finish by next frame. In contrast, our version asks the algorithms to report state by next frame, and it's okay not to finish computation by next frame. Why is it okay not to finish computation by next frame? First, as I will show later, it produces better streaming performance. Second, we found that the traditional definition of real-time is too myopic. Real-time should not be equivalent to running at 30 FPS. We argue that the sensor rate and the compute budget should be seen as design choices that can be tuned to optimize a downstream task. Third, attentional and adaptive algorithms might spend more budget on challenging frames, and the performance of such an algorithm cannot be simply measured by FPS. Last but not least, runtime is stochastic. A 30 FPS algorithm can still take longer time than 33 milliseconds for some frames, and we should build a robust system that can handle such situations. Our benchmark at time t queries the state at time t. At first glance, this instant response evaluation may seem unreasonable. No matter how fast the algorithm is, it cannot finish instantaneously. For example, if the algorithm takes time delta t to perform its computation, then to make a prediction at time t, it can only use data before time t minus delta t. We argue that this is the realistic setting for streaming perception, both in biological and robotic vision. Human vision systems associate the object across time and do forecasting. While human reaction time is 200 milliseconds, athletes are still able to catch balls traveling at more than 100 miles per hour. Similarly, streaming algorithms can also track and forecast to achieve better streaming performance. Therefore, tracking and forecasting naturally emerge under streaming evaluation. Our meta benchmark is a generic framework that can be used to convert any single-frame tasks to their streaming counterparts. We have experimented with both object detection and instance segmentation. For this talk, I will focus on object detection. Another access for benchmark instantiation is the compute platform, because our evaluation is runtime and thus hardware dependent. Here are 3 compute platforms we have experimented with, including the hypothetical infinite GPU setting, whose results are obtained through simulation. For this talk, I will focus on a single 1080 Ti GPU. So far, we have defined our meta benchmark. It's time to talk about solutions and analysis. All our experiments are conducted on Algoverse dataset with our own Coco-style annotations. The first step towards streaming perception is picking the right detector. If we run a state-of-the-art detector in the offline setting, we can obtain decent performance. When we switch to the streaming setting, accuracy plummets due to its high latency. A commonly adopted baseline is to run a fast detector that finishes before the next frame arrives, but we find that its output is too noisy. Based on our evaluation metric, we can find a middle ground where the solution has balanced accuracy and latency for the particular task at hand. This table summarizes results in the previous video. By comparing the first 2 rows, we can see that streaming perception is much harder than offline perception, which indicates a need for the community to focus on this ignored problem. And by comparing our streaming evaluation to standard evaluation, we can see that our metric quantitatively measures trade-off, and there exists an optimal sweet spot that maximizes streaming accuracy along the Pareto optimal curve. In addition to picking the right detector, we propose several ways to improve the streaming performance. I will talk next about scheduling and forecasting. Please check out our paper if you want to learn more about improvement with infinite GPUs. We noticed interesting effects of latency while exploring streaming solutions. Paradoxically, latency is sometimes minimized by sitting idle and doing nothing due to temporal quantization. In this example, after processing frame 1, the scheduler decides that frame 2 is already stale, and it waits for frame 3 to arrive before resuming the computation. In the paper, we provide a formal expression for exactly when it should wait, and should theoretically why is better. Note that this dynamic scheduler can be applied to not only streaming detection, but all other streaming tasks as well. For association and forecasting, we use asynchronous Kalman filter. I will skip the details here and show you some visualization instead. On the top is one without forecasting. On the bottom is the one with forecasting. We can see that forecasting can compensate some of the latency in streaming perception. Now we expand this table to include these additional improvements, and our final streaming AP is 20.3, still quite far from the offline AP of 38.0. Here are all the takeaway messages from this talk. In this work, we proposed a meta benchmark for streaming perception and provided several solutions and analysis to this problem. Please check out the paper for more details. Thanks for listening.